Why one sniper? Almost blacked out Silicon Valley's substation engineering. On the night of April 16, 2013, a team of unknown individuals breached the perimeter of the Metcalf transmission substation in San Jose, California. Over the course of 19 minutes, they fired more than 100 rounds of rifle ammunition into the cooling radiators of 17 massive power transformers. As thousands of gallons of insulating oil bled out onto the gravel, the transformers overheated and began to shut down. Silicon Valley, the technological heart of the United States, was pushed to the absolute brink of a catastrophic blackout. The local utility, PG&E, had to frantically reroute power at the macro grid level just to keep the lights on. It took 27 days to repair the damage. When the general public thinks about the power grid, they picture power plants and transmission lines. But the true choke points, the unsung fortresses that keep modern American cities from plunging into the dark, are the high-voltage substations. Today, we are looking under the hood of America's power infrastructure. We are going to break down the exact mechanical engineering of how these substations step down lethal voltages, how they use rare gases to extinguish plasma arcs, and how they act as the immune system for the largest machine ever built, the United States power grid. To understand a substation, you must first understand the physics of transmission. To move power efficiently across vast distances, say, from a wind farm in the Texas Panhandle to the suburbs of Dallas, engineers must crank the voltage to extreme levels, often 345,000 or 500,000 volts. High voltage means lower current, which minimizes the energy lost as heat along the wires. But you cannot feed 500,000 volts into a city block. It would instantly vaporize local distribution lines. The power must be stepped down. This is the primary job of the substation, and it is handled by the most critical piece of hardware on the grid, the Large Power Transformer, or LPT. An LPT is not a solid block of metal. It is an intricate, multi-million-dollar feat of electromagnetic engineering. Inside, massive primary coils of copper wire receive the incoming high voltage. Through the principle of electromagnetic induction, this creates a fluctuating magnetic field in the steel core, which induces a lower voltage in the secondary coils. But this process generates violent amounts of heat. To prevent the copper from melting itself into slag, the entire core and coil assembly is submerged in thousands of gallons of highly refined mineral oil. This oil acts as both a dielectric insulator and a coolant, circulating through massive exterior radiators. This is exactly what the Metcalf snipers targeted. By shooting the radiators, they drained the blood of the transformer. In the United States, replacing an LPT is an economic nightmare. They weigh upwards of 400,000 pounds. They are custom engineered for specific grid nodes, meaning there is no national stockpile of spares. If a major transformer in the PJM interconnection in Virginia blows out today, ordering a replacement from overseas will take anywhere from 18 to 24 months. Stepping down voltage is only half the battle. A substation is also the grid's immune system. Imagine a Category 4 hurricane sweeping through Florida, throwing a massive oak tree across a 230 kilovolt transmission line. The moment that tree bridges the gap between the wire and the earth, thousands of amps of fault current rush toward the grounding point. If this massive surge travels back to the substation, it will detonate the power transformer in a catastrophic explosion. To survive this, the substation must detect and isolate the fault in milliseconds. This is coordinated by protective relays, highly advanced microprocessors sitting in the control house. When these relays detect an anomaly in the current, they send an execution order to the high-voltage circuit breakers. But breaking a high-voltage circuit isn't like flipping a switch in your kitchen. When mechanical contacts carrying 230,000 volts pull apart, the electricity does not simply stop. it ionizes the air, creating a roaring bridge of plasma that can burn at 35,000 degrees Fahrenheit, hotter than the surface of the sun. You cannot blow this out like a candle. To quench this arc, American substations rely on specialized circuit breakers filled with sulfur hexafluoride, or SF6 gas. SF6 is a heavy electronegative gas that aggressively absorbs free electrons. The moment the breaker contacts open, high-pressure SF6 gas is blasted directly into the plasma arc, extinguishing a sun-level thermal event in less than 50 milliseconds. The fault is cleared. The transformer is saved. The rest of the city keeps its power, and it all happens faster than you can blink. All of this heavy iron and SF6 gas is orchestrated from the control house, the brain of the substation. Here, a system known as SCADA, Supervisory Control and Data Acquisition, constantly streams telemetry back to the grid operators. In the United States, regional transmission organizations like ERCOT in Texas or PGM in the Mid-Atlantic monitor this data in real time. The grid operates on a strict heartbeat of 60 Hertz. Supply and demand must match perfectly, second by second. If an AI data center campus in Ohio suddenly spins up a massive training run, pulling hundreds of megawatts of power, the SCADA systems register the voltage drop. Operators can remotely trigger motorized switches inside the substation, physically reconfiguring the bus bars to reroute power from a natural gas plant in Pennsylvania to cover the load. But this digital brain is the grid's second great vulnerability. While the physical hardware is protected by fences and cameras, the digital hardware is constantly probed by state-sponsored cyber threats. A compromised SCADA system wouldn't require a sniper rifle. A few lines of malicious code could theoretically command the circuit breakers to open, disconnecting a major metropolis from the grid entirely. High-voltage substations are the silent sentinels of the modern economy. They absorb the violence of nature, contain plasma hotter than the sun, and step down lethal voltages so you can safely charge your phone or run a billion-dollar corporate server farm. But as we discussed in our last video, the American grid is buckling under the weight of the AI revolution. We need thousands of new, upgraded substations to handle the massive influx of load. Yet we are facing historic shortages of transformers, heavy electrical hardware, and the specialized civil engineers required to build them. The physical mechanics of our power grid dictate the limits of our economic growth. The infrastructure we rely on today was built for a different century. Upgrading it will be the most expensive, complex engineering challenge in American history. If you want to understand the macroeconomic impacts of this infrastructure deficit and how it is shifting global capital, hit the subscribe button. In our next video, we will break down the exact economics of the interconnection queue and why trillions of dollars in clean energy are currently trapped on paper, waiting for a connection to the grid. Until next time, this is USA Grid Mechanics.